Welcome to The Explainer, where we take on those tricky topics and make them make sense.
So, if you've ever dipped your toes into organic chemistry, you've definitely felt this pain. Drawing out every single carbon, every single hydrogen. It's slow, it's messy, and when you get to bigger molecules, it's a complete nightmare. But there is a much, much better way.
You're not alone in thinking this is a bit much. Chemists got tired of it too, and they came up with a seriously elegant and powerful shortcut to cut right through all that chaos.
All right, first up, let's tackle the drawings themselves. The actual blueprints. How can we sketch these things out in a way that's quick, clean, and, well, how the pros do it? Okay, so this method of showing every single atom, it's called a full structural formula. It totally works, technically, but man, is it inefficient. Imagine chemists trying to brainstorm a new reaction, and they have to draw all this out. It just grinds everything to a halt. It really is like trying to write a whole novel using only big, clunky block letters.
So, let's get you in on the secret. Let's learn the code that chemists use to talk to each other, quickly and clearly. It's called the skeletal formula, and honestly, it's about to completely change how you look at molecules.
The whole idea here is that we're going to stop drawing individual atoms and start drawing the carbon skeleton. Think of it like a new visual language, and it's built on just a few simple, really logical rules. Once you get them, you'll be reading and writing chemistry like you've been doing it your whole life.
And the beauty of this whole system is just how simple it is. You see a corner in a zigzag line? Bam, that's a carbon. The very end of a line? Yep, also a carbon. And we just assume each of those carbons has enough invisible hydrogens to make 4 bonds. The only things you have to draw are atoms that aren't carbon, or hydrogens attached to something that isn't carbon. That's pretty much it.
Just look at this difference. On the left, we have propane with all 11 atoms explicitly drawn out. On the right, it's just a clean, simple little zigzag. That's it. This endpoint is a carbon, this corner is a carbon, and that endpoint is a carbon. 3 carbons total. The hydrogens, we just know they're there. It's so much cleaner, faster, and there's zero confusion.
And this shows you exactly how we deal with other elements. So here we have pentan-2-ol. The 5-carbon chain is just that simple zigzag again. But the important part, right? The functional group, that OH, the alcohol, is still drawn right in. So you get all the critical info you need just without any of the clutter.
Okay, so drawing these things is one half of the puzzle. But what about naming them? If I draw a molecule here in this studio, and a scientist in Japan draws the very same one, how do we make absolutely sure we're calling it the same thing? We need a universal name, right?
Well, let's look at how that problem was solved. We need to talk about the IUPAC system. You can think of it as a global grammar for chemistry. It's the system that makes sure everyone is speaking the exact same language.
The goal here was absolutely massive. They wanted to create a set of rules so logical, so precise, that any chemist on the planet could look at a name and draw one and only one possible structure. No guesswork, no ambiguity, period.
Now, to get this language, you don't have to go out and memorize a giant dictionary. Nope, you just need to understand its grammar. And the key is breaking down any name into its 3 basic parts.
And I love this analogy from our source material. It's perfect. Think about those really long, formal historical names. Each part of that name tells you something, right? It tells you about family, or where they're from, or their title. Well, it's the exact same idea for a chemical's IUPAC name. Every single piece tells you something very specific about its structure.
So, every standard IUPAC name is built from these 3 parts. You've got the word root in the middle that tells you how long the main carbon chain is. Meth for 1 carbon, eth for 2, but for 4, and so on. Then at the very end, you have the suffix. That identifies the molecule's main family, like ane for a simple chain or ol for an alcohol. And finally, everything at the beginning, the prefix, describes all the other stuff, all the branches and little attachments and where they're located.
Okay, but this is where the system gets really, really clever. What happens if a molecule has a couple of different things going on? Like, what if it could be an alcohol and a ketone? Which group gets to be the main event, the one that gets the fancy suffix at the end? How does the system decide who's the star of the show?
Well, it all comes down to a hierarchy.
IUPAC basically made a priority list, a ranking of all the functional groups. This ranking is usually based on chemical properties, like the oxidation state of the carbon. So, for example, a ketone group outranks an alcohol group because its carbon is more oxidized, making it a more, let's say, important feature. The highest ranking group on the molecule gets to be the main character. It gets that coveted suffix name. Everything else, well, they get demoted to side characters and are named in the prefix. That's why an OH group is an ol when it's the star, but it's just a hydroxy group when something more important is on the molecule.
Okay, theory time is over. Let's put this all into practice. We're going to combine our new drawing and naming skills, and we'll walk through the whole process, step by step, for naming a molecule right from scratch.
If you follow these 4 simple steps, you can systematically break down and name pretty much any organic molecule you come across. So step 1, find the longest continuous chain of carbons. That's your foundation, your word root. Step 2, number that chain. The key here is to start from whichever end gives all the attachments the lowest possible address numbers. Step 3, you identify every single thing hanging off that main chain. Those are going to be your prefixes. And finally, step 4, you just assemble the name like a puzzle, putting the prefixes in alphabetical order right before the root and suffix.
So let's try it with the name you see on the screen. 3-chloro-2-methylpentane. The trick is to work backwards. The end of the name, pentane, tells us 2 things. Pent means a 5-carbon chain, ane means it's a simple alkane, no double bonds. Then, the prefixes tell us there's a chloro group on carbon number 3 and a methyl group on carbon number 2. Now here's the crucial part. Chloro comes before methyl in the name, not because 3 is bigger than 2, but because C comes before M in the alphabet. You always list the prefixes alphabetically.
And just like that, you now have 2 incredibly powerful new tools in your toolkit. You've got the secret code of skeletal formulas, so you can draw structures like a pro. And you have the universal grammar of IUPAC, so you can name them with perfect precision. You can literally transform visual chaos into pure logical structure. That's your new chemistry superpower.
And at the end of the day, that's why this matters so much. This isn't just about memorizing rules for a test. This is about becoming literate in the language of matter itself. Learning this language is the very first step to truly understanding the molecules that make up our food, our medicine, our bodies, our entire world. It's the key to finally understanding the incredible molecular conversations that are happening all around us, all the time.